In the next two videos, we will look at TensorFlow and Keras, which is the fourth topic of deep learning. This video is part 1, and we will look at multiple ways to build neural networks using TensorFlow. Now that we've looked at optimizers and error backpropagation in the last two series, we're ready to implement basic neural networks. In the artificial neural network series, we roughly built a neural network using numerical differentiation without backpropagation. From now on, we will implement accurate neural networks using automatic differentiation and backpropagation. We will use TensorFlow and Keras, the most widely used tools for implementing neural networks. This video was produced in Korean and translated into English. My voice was generated by AI, text-to-speech. Let's take a look at the full table of contents. In the first video, we will look at how to build neural networks with TensorFlow. And in the second video, we will look at how to build them with Keras. Let's implement binary classification, multiclass classification, and regression models using TensorFlow and Keras. There are many ways to implement neural networks with TensorFlow and Keras. Here we will use 7 ways. In this video, we will use TensorFlow, and in the next video, we will use Keras. Let's look at 3 basic ways to implement feed-forward neural networks using TensorFlow. Let's create a simple neural network model, as shown below. This neural network can be expressed as the following function y hat. Since x are data points' constant values, y hat is a function of w and b. Set w and b as variables in TensorFlow. W and b are updated during the training process to minimize the loss function through error backpropagation. Initially, variables w's are randomly initialized and variable b's are initialized to 0. A more efficient way to initialize w will be covered in more detail later in the series on weight initialization. For now, let's simply initialize them to random values. If you input the data x into this neural network and perform forward propagation, you can get the y hat value. Let's use the following 3 methods to update the parameters of a neural network in TensorFlow. The first method is the most basic type and uses gradient tape and gradient descent. Gradient tape is an API that performs automatic differentiation in TensorFlow. We looked at the automatic differentiation in detail in the series on error backpropagation. Construct a computational graph as shown on the right, and follow the reverse direction to find the gradients of the loss L with respect to each parameter. We then update each parameter using gradient descent. The second method is to use gradient tape and the optimizer. We looked at optimizers in detail in the second series. When you create an optimizer and use its apply gradients function, each parameter is updated using the gradients obtained with gradient tape. This allows you to improve the performance of the neural network by applying various optimizers to the above code. The third method is to use the optimizer's minimize function. This updates the parameters to minimize the loss. The minimize function uses gradient tape internally to perform automatic differentiation. This makes coding a little more convenient than the code above. There are also many ways to implement neural networks using Keras. We will cover this in the next video. Let's implement a binary classification model using the first method. Import TensorFlow as TF. Generate a dataset for binary classification like this. Then split it into the training and the test data. Visually see the distribution of data points. Create a neural network as shown on the right. Since there are two features in the data, the number of input neurons is 2. And since it is a binary classification problem, the number of output neurons is 1. The number of neurons in the hidden layer is set to 8. And the learning rate is set to 0.05. Create and initialize TensorFlow variables for the parameters of each layer. The weight of the hidden layer is a 2x8 matrix, and the bias BH is a 1x8 matrix. And the weights WO of the output layer is an 8x1 matrix. And the bias BO is a 1x1 matrix. WH and WO are initialized randomly. And BH and BO are initialized to 0. Place the parameters created this way in the parameters list. Next, we write a function to calculate the loss function. Since it is a binary classification problem, binary cross-entropy loss is used. Next, we write a function to calculate the output of the neural network. When the data X is input to the neural network, forward propagation is performed to calculate Y hat. The activation function of the hidden layer is ReLU, and the activation function of the output layer is sigmoid. Return the sigmoid output as is or the predicted class. Next, we write a function to fit this neural network to the data. Let's update the parameters using the mini-batch method. Randomly sample batch-sized data points from the training data. We then use gradient tape to perform automatic differentiation to find the gradients of the loss L with respect to the parameters. Then, we use these gradients to update the parameters using gradient descent algorithm. The assign subfunction of a TensorFlow variable object updates parameters in this way. Repeat this process. This is the standard gradient descent formula. Then we calculate the loss for training and the validation data. This has nothing to do with training. It's just to observe changes in loss during repetitions. Now we call the fit function to train the neural network. Enter the training and the test data into the fit function. The number of iterations is set to 200 and the batch size is set to 50. Once training is complete, visually see the loss history. Finally, we measure the accuracy of the test data. Let's check the results. The training data consists of 2 clusters like this. Red data is class 0, blue data is class 1. You can see that the losses of training and test data gradually decrease during 200 iterations. Visualizing this, it looks like this. The accuracy of the test data is 0.92. In the artificial neural network series, we approximately implemented a binary classification model using numerical differentiation. Using automatic differentiation with gradient tape in TensorFlow, we can implement an accurate binary classification model like this. Let's run this code. The results are as follows. Next, let's implement a multi-class classification model using the second method. To apply the optimizer, import TensorFlow's optimizers class. For multi-class classification testing, we generate a dataset consisting of 3 clusters like this. The class of y is 0, 1, 2. We one-hot encode this, split the data into the training and the test data. Create a neural network model like this. Since this is a multi-class classification problem, the number of output neurons is 3, which is the number of classes y. Real U is used as the activation function of the hidden layer, and softmax is used as the activation function of the output layer. Create and initialize TensorFlow variables for parameters. Create an atom optimizer. There are various optimizers available, including Attograd and RMSProp, etc., but here we will use Atom. We looked at the optimizer in detail in the second series. Since this is a multi-class classification problem, we use cross-entropy as the loss function. You can apply the optimizer like this for updating parameters. This applies the atom optimizer and updates the parameters using the gradients calculated above. Let's check the results. The data is organized into 3 clusters like this. You can see that the losses measured with the training and the test data gradually decrease. The accuracy of the test data is 0.92. Let's run this code. The results are as follows. Next, let's implement a nonlinear regression model using the third method. Generate a sinusoidal dataset mixed with Gaussian noise. Split this data into the training and the test data. Then we generate a dataset to estimate the sinusoid as follows. After training is complete, when XPred is input to the neural network, a sinusoid with noise removed will be output. Create a neural network like this. The number of neurons in the output layer is 1. A hyperbolic tangent activation function is used in the hidden layer, and a linear activation function is used in the output layer. Like the previous code, we create and initialize TensorFlow variables for the parameters. And we create an atom optimizer. Since this is a regression problem, we use the mean squared error loss function. Next, let's look at updating parameters. The optimizer's minimize function calculates the gradients of the loss and updates the parameters. This function performs gradient tape internally to calculate the gradients. The minimize function makes coding simple like this. If you want to handle the gradient before updating the parameters, you'll need to use gradient tape and the optimizer just like in the previous code. Let's check the results. Over 200 iterations, losses are decreasing significantly. And the results of estimating the data points in XPred are as follows. The sine curve is clearly visible. Let's run this code. The results are as follows. So far, we have implemented several neural network models using TensorFlow in 3 different ways. In the next video, we will implement neural network models using Keras.